group today, we'll be presenting about spectrophotometric titration. Here, I am Sumita Anna Prabha Balachandra with nomometric 147087 would like to present about the meaning of titration and the laws that involved in spectrophotometric titration. First of all, titration is a process that determining the quantity of substance A by adding measured increment of substance B, the titrant, with which it reacts until chemical equivalence is achieved. Before we look at the meaning of spectrophotometry, my friend will be explaining about that. So I will be explaining about the laws that involved in the spectrophotometric titration, which is known or considered as the principle as well. So Beer's law and Lambert law is the laws that involve. So Lambert law states that there is a direct but non-linear relationship between the length of the light pass through the cuvette, which is known as the sample L, and of the light transmitted. LO is the intensity of light entered before and after it passed through the sample. Therefore, T is equal to LT over LO. Beer's law states the light absorbance depends on solid concentration. The combination of Beer's law and Lambert law, known as Beer-Lambert law, states the absorbance depends on solid concentration, molar absorptivity or absorption coefficient, and length of the light path. Therefore, absorbance is equal to molar absorptivity, length of light path, and the concentration of the solute.
Assalamualaikum and hello. I'm Amir Aizuddin bin Azmi with metric number 146820. I'll be talking about the types of spectrophotometer and its application in spectroscopy world. Alright. So the types of spectrophotometer is visible spectrophotometer, ultraviolet visible spectrophotometer, infrared spectrophotometer, fluorescent spectrophotometer, and atomic absorption spectrophotometer. Alright. So there are various applications of spectrophotometer in spectroscopy world. It is useful in qualitative analysis, especially when identifying classes of compounds, both biological and pure state. Alright. And then the spectrophotometer is essential in quantitative analysis of biochemistry, such as determining the unknown concentration of a given species through absorption spectrometry. A perfect example is the nucleic acid in a protein. And then spectrophotometry is to identify the molecular weight of a particular sample, such as peak rate in amines, ketone compounds, aldehyde, and sugar. Alright. And then other applications of spectrophotometer are identifying impurities, detecting the concentration of substances, organic compounds, structure elucidation, identifying the characteristics of a protein, identifying the dissolved oxygen content in a body of water, analysis of respiratory gas in hospitals, and functional group detection.
Greetings doctor, my name is Yasmin Nadira and I will explain about spectrophotometric titration. So spectrophotometric titration is used to determine the endpoint or to determine the quantity of sample by adding measured increments of a titrant until the endpoint, in which the endpoint indicates that all of the sample has reacted, hence the endpoint is reached, while the equivalence point can be detected visually either by color produced by an indicator or by the color of the reactant. The instrument used is spectrophotometer, in which to measure the intensity of wavelength in the spectrum of light. For the experimental technique, it starts with the solution to be titrated is taken in the cell, then the cell is kept in the light path of a spectrophotometer and adjusted to the wavelength at which the experiment is to be carried out, and this instrument is set to 0 absorbance or to some other starting value that lies within the range of the linearity of the instrument. After that, a known volume of titrant is added and the absorbance is read again. This is repeated at several points before the endpoint and several points after. Finally, the absorbance is plotted against the volume of titrant added, and from the graph we can obtain the equivalence point. Assalamualaikum and hi, my name is Nur Atika binti Maisah. My metric number is 148788. So now I will continue with the basic principle of spectrophotometric titration. Okay, in this spectrophotometric titration, the absorbance is directly proportional to the concentration. It is because when the titrant is added, the concentration of the solution will change. Based on the formula of absorbance is equal to epsilon Bc, when the concentration is changed, the absorbance also change. So that it proves that the absorbance is directly proportional to the concentration. In this spectrophotometric titration also, the endpoint of the titration can be obtained from the graph of absorbance against volume of titrant added. However, the type of graph is always depending on the adsorption capacity of the three important things, which is titrant, analyte, and product. There are a various type of graph or curve based on the different condition. Firstly, the analyte absorb while the titrant and product not absorb. Second, titrant absorb while analyte and product does not absorb. And the third is product absorb while analyte and titrant not absorb. And the last one is the titrant and analyte absorb while the product are not absorbed. Okay, in the whole spectrophotometric titration, the curve of graph is very important. So now let's look at the first condition, which are when analyte is absorbed while titrant and product not absorbed. As we can see here, the initial state of the absorbance will be at the maximum state as the analyte is absorbed. Then while the titrant and product is not absorbed, so absorbance will be decreased until the endpoint. Since the product is not absorbed, so the absorbance will be constant here. Next situation is when the titrant absorbed while analyte and product not absorbed. As we can see here, as the analyte is not absorbed, so it will start at the minimum point of absorbance. And then when we add the titrant, the product is not absorbed. So our absorbance is still at the constant line. And then when we add more titrant, since our titrant is absorbed, so absorbance will increase. For the third situation, which is our product is absorbed while analyte and titrant is not absorbed. As we can see here, as the product absorbed, the absorbance will increase until the end point, but then the analyte and titrant is not absorbed, so our absorbance will be constant here. For the last situation is when the titrant and analyte are absorbed while the product are not absorbed. So as we can see here, as the product are not absorbed, our absorbance will decrease until the end point. But then the titrant and analyte are absorbed. So at the end point, the absorbance will increase. So that's all for me. Thank you.
Let's go to the example question. Let's go to the question 1. The stroke graph is the graph that represents where the endpoint was estimated spectrophotometrically. So, which graph that shown if the analyte and the product has zero absorbance? Explain why. So the answer is this graph represents when the product and analyte has zero absorbance. Why? It means when the reading started, the product analyte is colorless, so it has zero absorbance. And when more titrant and titrant was added into the solution, so it resulted in increasing absorbance. Question 2. A satisfactory endpoint of spectrophotometric graph must obey Beer's law. Hence, for the volume changes due to the volume addition of a titrant must be corrected. Question is, the absorbance of ATA after adding 120 microliter to 1.6 milliliter of copper 2 is 0.256. Calculate the corrected absorbance. So how we are going to find the corrected absorbance? The corrected absorbance, we will use the formula of corrected absorbance equal to the total volume and divide by the initial volume and multiply with the absorbance measure. So the total volume that we will get is 1.72 exponent negative 3 liter after we convert all the unit to liter. Then we insert into the formula, which is the total volume 1.72 exponent negative 3 liter divided by the initial volume, which is 0.0016 liter, and multiply with the absorbance ratio, which is 0.256, and the answer will be 0.2752.